Good afternoon, my name is Stephanie Martinez and I will be presenting my subsystem called Structural Component Design of the Biofeedback Device to help manage stress using physiological measurements for my Capstone 1. Here we have the technology assessment. This is some information that I found on the internet about neurofeedbacks with beta and theta training for anxiety and depression, and some EEG biofeedbacks to implement in the headphones that we will be using. The first subsystem is I called it the ergonomic ear cups. It's this headphones that we see right here. We have our MOPs, the dimension, the volume, we have volume, mass, depth, width, and height. And the operational objective of this subsystem is that the ear cups are designed to fit comfortably over the ears. They're going to be made from soft, hypoallergenic, breathable materials that minimize discomfort during the prolonged use, since we estimate that the average client or patient will be using these headphones maybe all day long, so we do want to minimize the discomfort for the prolonged use that they will be using the device. And the interior of the ear cups will include the sensors for the physiological measurements to detect that stress. It will have sweat, TSR, the EEG, brain waves, it will have oxygen levels, heart rate, everything that the physiological measurements will measure when you have that stress. I wanted to include some materials that we could use for this subsystem. So we have memory foam, which a lot of headphones and companies that do headphones use memory foams to provide comfort and enhance the fit and the ear shape of each patient. Then the other material that we will want to use is protein leather because it is hypoallergenic, and we do want every material to be hypoallergenic because there is some patients that are sensitive to some materials and fabrics, and we do want that patient to do have some hypoallergenic materials so their skin won't get irritated, and soft silicone because it's yet again hypoallergenic and easy to clean. So we have our second subsystem. This is the adjustable headband. As you can see, it's still a headphone, just adding a headband. We have the MOPs, which is volume, mass, depth, width, and height, just like the first subsystem. And this operational objective is that the headband will be adjustable and padded, securing the fit for different head sizes. And instead of having the sensors on the ear cups like the first subsystem, this subsystem will have the sensors on the headband, making it more secure and more into the skin so that we can have more reliable data on the stress levels and how to manage them. It will include all the sensors. It will include the PCR, the sweat, heart palpitations, the oxygen levels. It will have everything just on the headband, and the headphones will be used to manage that stress. I made another table for the materials that we will want to use. The first one being ABS plastic. So ABS plastic is used majority of the time because companies like to use ABS material because it's lightweight and durable to make the headphones. So a lot of the headphones that we see out in the open, they are made probably from ABS plastic. And memory foam padding, again, because it offers comfort and is hypoallergenic and nylon fabric that provides strength and flexibility. So we have our third and last MOP subsystem. This one is more like the first one. It is a headphone, but it's going to be a compact headphone. And what is the difference? Okay, so our compact headphones, we will have them within the ear cups, and they will contain the necessary electronics for data processing. So this is more on the electronic side of the structural design, and it will include microcontrollers and Bluetooth modules for wireless connection. It's the same as the first subsystem, just a little bit more electronic. We do have the MOPs, you can see the dimensions and the values, and for the materials we will want to use, if the pub matrix decides that this will be the best highest score, will be once again ABS plastic. It's lightweight and durable, and a lot of the headphones that we see outside, they are made of ABS plastic. Silicone seals. So instead of memory foam, we will use silicone seals on this because they are even more electronic wise. So we want the heat transfer to not be as much as when we have the memory foam padding, because it will get burned and stuff because it is more electronic driven. And aluminum alloy because it offers a robust lightweight casing, also adding that heat dissipation that we want to use with the silicone seals. Now we have the pug matrix. In this pug matrix, we can see the adjustable headband scored the highest. So how we do this pug matrix was at the weight, the comfort, the durability, breathability, hygiene, waterproofing, flexibility, and impact resistance. So we can see that the compact headphones and the adjustable headband are pretty there similarly, but the adjustable headbands are the highest score, so we will go with the adjustable headbands. That was their second subsystem. So now that we have that in mind, and we do want to make the headband headphones, this is the subsystem architecture and how we're going to make that, and add it with the sensors and the and the electronic side and data programming of the headphones and the stress management. So the headband frame will be the main structure, providing support and durability, and then we do the adjustment mechanism that allows the user to customize the fit of the headband. The padding layer ensures comfort against the head, and the covering material, the nylon and chain leather, offers a finish that can enhance aesthetic and comfort. It's more of an aesthetic type. And then we have the hinge mechanism that facilitates the movement and the flexibility of the headband. And the mounting points will add the location where the sensors will be attached, ensuring stability and functionality for the headphones. Now for that, we did some calculations. I did want to do some heat transfer because it is really important, since we don't want any heat coming to the patient and happening something that we don't want, or the headphones melting. So we did some heat transfer calculations. We did the thermal conductivity, the surface area, the temperature on one side and the other side, and the thickness of the material for the foam, for the area of the ear pads, the body temperature, the ambient temperature, and the thickening of the padding if we're going to use memory foam. So this is what it gave us. It gave us 0.06 of heat from the user's body through the padding material of the surrounding environment. So low heat transfer means the headphones should remain comfortable for extended time of wear. They will not heat up, and they will not heat up due to the person's body heat. And it highlights the importance of selecting materials that minimize heat transfer. So we will be good on that side. We also did some calculations for the battery life of the headphones. This is pretty important since the patient's going to be using it pretty much frequently all day. So we assumed the battery capacity was 3,000, and then we made the battery life calculations, and it gave us 14.8 hours. So it would technically be 15 hours of sustained stability battery life for the headphones. It would allow the patient for all day use without going and frequently charging the headphones. And for the marketing competitiveness of this, it's pretty good because long battery life can be a significant selling point in the competitive headphone market. A lot of people hate the idea of having headphones and having to charge them frequently, so having some headphones that will manage your stress and give you an accurate data of how your stress levels are being, and then having 15 hours of battery life would be amazing for the market competitiveness and the patient. We also did some subsystem calculations of the natural frequency. The simple harmonic oscillator, it gave us 5.03 hertz, and what the frequency is, natural frequency is, it indicates the frequency at which the headphone system will naturally vibrate. Okay, so if there's some loud noises outside and the headphones are doing what they're supposed to do, the lower natural frequency suggests that the headphones may vibrate on lower frequencies that would affect the sound quality and comfort. So if the natural frequency is close to the frequency of common sound like music or outside noise, it could lead to resonance. We also did some free body calculations. This is really important for the durability of the headphones. We calculated the weight, the normal force, the friction force, and the tension of the headphones, which gave us an analyzation of the free body diagram, and then it reveals how the interaction with the forces acting on them when worn. So we want to highlight the importance of the weight and normal force and friction and tension to ensure that the headphones are stable and durable and remain comfortable during the process of effectiveness of the headphones. We also did some alternative cone-ups for the design of the headphone, but we wanted to be more on the how we're going to make it side, if we were going to inject some type of chemical or we were to sew the entirety of the headphone. So here are the cone-ups, the three alternatives of injection, sewing, or both. So the first cone-up is polyethylene injection. We will inject polyethylene to a headphone mold, and we will make the skeleton, like this part here, we will make the skeleton of the headphone, the headband, mostly of polyethylene, and then we will sew the memory foam for the ear cups to optimize and to minimize waste during the injection and reduce production costs. The second alternative was ABS material, the one that everybody uses to make headphones, and we will do the same. We will inject the mold and make the functional headband become durable and last more, since headphones usually do have ABS material on them. The third alternative is all sewed memory foam, no injecting, no chemicals, just an all memory foam padded headphone that adapts to the head and aims to provide premium listening experience by comfort, sound quality, and durability. So we did a PUD matrix for the three alternatives: the sewing, just sewing fabric and padding, the injecting of the hypoallergenic mold, and the hybrid injection and fabric. So here we can see that the two best options are only the injection and the hybrid fabric mold. What I chose was to do the hybrid one, since just only the injection of the mold won't have that comfort on the ear cups for the patient, since it will just be plastic. So we don't want the patient to become uncomfortable and could heat up more, since it's just a lot of plastic for the headphones, and then we will sew memory foam onto the padding, so we can add the sensors here, and you can listen to what the person has to say to get use on that physiological measurements and stress. We did another pug matrix for the materials that we're going to use for the injecting and the padding. So we have polycarbonate, we have ABS, polypropylene, silicone, EVA, nylon, and polyethylene. So polyethylene and polypropylene were the highest scores, but polyethylene is not hypoallergenic. Polyethylene is hypoallergenic and it costs less. So we want to use polyethylene since we do want the patient to not have irritated skin or rashes, because a lot of people are sensitive, and we do want to use the best materials on the market. Even if it costs us more, we will still use it. So here we have the cost technique of operation. So this is a summarized table of the costs associated with the sewing of the memory foam and the injection of polyethylene for the headphone production. So we have material cost, labor cost, overhead cost, and the total estimated cost for the sewing and injecting of the polyethylene mold. Here we have some risks and mitigations of the polyethylene injection on the headbands. So some of the risks are material brittle at low temperatures, because the polyethylene can become brittle when on cold conditions, but for that we will have to use a high density polyethylene variant or blend with other plastics to improve their performance, but we do think just using a high density polyethylene would be the best option. Another risk is the deformation on high temps. Polyethylene may deform melt at high temperatures, but since we did the calculations and it gave us 0.6 watts, we do think it's not going to be a problem since it's not going to heat up a lot. But if it does happen, we will ensure the headphones operate within the temperature range suitable for polyethylene. Another risk is the UV degradation, because prolonged exposure to UV light can degrade polyethylene. So for that, we will add UV stabilizers to the polyethylene or use a protective coating on the outer of the headphones. Another risk is the chemical resistance, because polyethylene may react with certain chemicals. We will avoid exposure to hard chemicals or use a polyethylene variant with enhanced chemical resistance. Now the sound quality is another risk, because polyethylene might affect the acoustics of the headphones, but we will design and test prototypes to extensively ensure that the material does not adversely affect sound quality. The production cost is another risk, of course, but polyethylene may not be cost effective for small product runs. We will want to design and test prototypes to ensure the material does not be more expensive. So for that, we will want to maybe buy in bulk sizes. It's way more cheaper. The recycling and environmental impact. Polyethylene can pose environmental concerns, but for that we will use recycled polyethylene or ensure the design allows for easy recycling of the headphones. And the last risk is color and aesthetic. Achieving the desired color and finish with polyethylene might be challenging, but we will use additives and surface treatments to achieve desired aesthetic properties. We have another subsystem risk and mitigation assessment for the memory foam. So the material degradation is one of the risks, because memory foam may degrade over time, especially with all the sweats and oils that the person will have. We will use high quality durable memory foam and consider treatments to resist the sweat and the oils. Another one is allergic reactions. Some users may be allergic to memory foam, but we will use, once again, hypoallergenic materials. The comfort is an issue. Poor design or material choice may result in discomfort. We will test different foam densities and fabric types to find the most comfortable combination for the headphones and the user. The durability and wear is another risk. It may lead to wear and tear and reduce the lifespan of the headphones. We will reinforce stitching and use durable fabrics to extend the lifespan of the foam pad. And the sound isolation is another risk, because improperly designed pads may affect the sound isolation. And the quality. We will design and test prototypes for optimal sound quality. The production cost is another risk as well, since high quality materials can increase production cost, but we will optimize design for efficient material and consider, once again, buy them in bulk because it's way more cheaper. The heat retention. Memory foam may retain heat, but for that we will use breathable fabrics and perforate foam to improve ventilation and reduce heat retention. Cleaning and maintenance. Foam pads may be a little bit difficult to clean, but we will choose washable materials or design covers that can be easily removed and cleaned, and they will be sold separately. Consistency in production. We will implement stringent quality control to measure and ensure the consistency across all produced pads. So here we have the references that I used. They're mostly about the chemical reactions of polyethylene and memory foam and the comfort. And here we have the project planning for this Phase B and our Phase C1 presentation. Thank you so much. That's it for me today.